Ladies and gentlemen, boys and girls, quick one. Do we know how photocopiers work? Do we know how touchscreens work? What about electric spray painting? Do we know how they work? Come over, let's talk about this. These are some of the gadgets that use electric fields. We have a photocopier, how that ink sticks on that paper. We have electric spray painter, how that paint is able to stick on the body of the car. We have the touch screen. What happens when you touch that plastic, that metal, that makes you click an icon and you can operate your smart gadget? Today, I want us to discuss something that is very instrumental in this electric field. What is electric field? These are invisible regions where charges exert forces. In other words, an electric field is a region in which charged objects experience forces. Before us is a simple simulation to help us understand about electric charges. Remember, the electric field lines do not cross each other and they move from the positive point charge to the negative point charge. Similarly, what happens if you have a positive and a positive? There is repulsion, and we can see repulsion around this region here, that the negative and the positive have attraction between them. This is the basis of how those machines we talked about works. So let's move a step ahead and see what happens next. We have said that electric fields are the regions where force is felt, and this force is felt by charged bodies. Now, let's talk about electric field strength. What is electric field strength? This is the force per unit positive charge on a stationary point. So we can simply say is equal to that force over charge, mathematically speaking. Similarly, in a uniform field, at what force does it experience in that field? In a uniform electric field, the electric field strength is given by the change in potential over the distance separating the two plates. Let's talk about point charges. What brings us to what we call the Coulomb's law. Coulomb's law talks about there is a charge at a particular point and another one at a particular point, and the distance separating them, we give it letter R. We say the force being experienced in this kind of field is directly proportional to the product divided by the square of the distance between them. Remember, if it is two spheres, we take it from the center of one sphere to the other. If we replace the proportionality sign, we find that F is equal to Q1 Q2 over 4 pi epsilon naught R squared. Remember, epsilon naught is what we call permittivity of free space. There is a value you will always be given this one in an exam situation. We talk of the work that is supposed to be done to get a charge from a given point. That point we talk of infinite point at zero potential. To bring that charge from a particular level, a particular point, to where it is required. This is the target area. Let's talk about the target area. The target area. This is at infinity. We talk of electric potential. How much work should be done to bring that from the infinity to the target point? This potential is given by epsilon R. Now that gives us what we call the electric potential energy. We denote by EP is because we have the 2 points as per the Coulomb's law. We shall talk of Q1, Q2 over 4 pi epsilon R. Just the distance, not squared. Please get the difference between the Coulomb's law and that gives us the force, and how to get the electric potential energy between the two charges. These are basically the equations that you will need if you want to thrive in this concept of electric fields. If you want to know more about this, to go deeper, advanced, don't hesitate. Subscribe